All right, welcome back, everyone. So today there's gonna be two talks by me. The first one is going to be about setting up a private experiment. Primarily, if you have things that you do not want necessarily to share with everybody else in the ratpac community, you could put it there. And the other talk is going to be about Chroma, which is this GPU accelerated photon simulation toolkit that could work with ratpac-two. You could do so. All right. So setting up a private experiment. The motivation, as I just sort of briefly described, is that this whole design concept with this whole design concept of ratpac-two is that you're supposed to have this core repository that's shared and open source with everybody, and so that a lot of the code that you're gonna have to rewrite for every single experiment can live in that code, and people new coming in don't have to necessarily go through that process and adding those same features again. But you also want these experiment specific code to have somewhat exist, and you don't necessarily want everybody to have access to that. And so the design of ratpac-two is made such that we're allowing both of these two things to exist at the same time. So just some examples of code that, in my opinion, should go into ratpac-two, for example, is if you have a dark room setup or something like that, and you measure some PMT information, publicly available, commercially purchasable PMTs, and you might want to have that paper out, and then you have that data sheet of your measurements for the PMTs into ratpac-two if you desire. Some common materials like scintillator, cocktails, stainless steel stuff you build a detector with. Those material properties could potentially also go into ratpac-two. If you're writing some generic waveform analysis code that's not specific to your experiment, just some sort of code that analyzes digitized waveforms coming off of PMT, for example, or some filter code reconstruction code that you would like to share with everybody else, that's a good place to put that too. And you can, as we went through, there's a couple examples where these filters and waveform analyzers already exist in ratpac through the process of us developing ratpac-two primarily for EOS and among other experiments in the past as well. Some good example of code that might want to go to a private experiment are stuff like perhaps you have some complex geometry for your detector, and every detector's geometry is going to be slightly different. And in the workshop, we've worked a lot about other detector geometries as well. And so that you might want to, we might want to put that in a private experiment where that doesn't interact with anybody else. Some calibration data related to your detector could also go in there. And I'll go through some examples of how we do this in EOS. And there's also perhaps also pipelines for processing raw data. So yesterday I talked about HDF5 production and stuff like that, but it's also very detector specific. So you could also put that in a private experiment and not interfere with ratpac-two. So in this talk, I'll go through sort of the generic process of how to set this up for any experiment you want. We aim to make this process as simple as possible. And I'm also going to talk briefly about what we do specifically in EOS and also some lessons we've learned from doing that. All right, so as promised, how to set up a private experiment. So we do have a template set up in GitHub for how to configure a ratpac experiment. And just so you guys know, this is not some abandoned project that we just put out there 10 years ago. The continuous integration that ratpac does on GitHub ensures that this experiment can be built for every commit of ratpac-two. Otherwise, we'll have a test failure. So this is consistently being checked to make sure that it works with the current release version of ratpac-two. And so you should feel reasonably confident that this will work for you reasonably well. Basically, there's a button on GitHub. I guess I could show this just really quickly. So this is the ratpac experiment repository. And you can just click this button that says use template and you create a new repository, configure whatever you want with that. And this is slightly different from forking the repository because you're not that new repository you create is not necessarily connected to this template repository. So you can sort of do whatever you want without having to worry about what we're doing with this configuration specifically. So that's pretty useful. And then in this template, there's a script just on the top level called rename.sh, and you can rename it to be whatever you want. In EOS, we call our private experiment EOS simulations. It could just be whatever alias you would like to have your experiment be called. And so what changes is that once you've done that, you can compile this specific experiment, and it will create a new executable, and you will run your macros using that executable rather than rat. So instead of using rat for EOS, we will use EOS as the executable that runs all your macros, and that will include all the information from the private experiment. RATDB information, the extra processors you've written, stuff like that will all be there. So I don't like giving people advice about how to write code unless I have to review the code. But just some couple of advices that perhaps would be universally acceptable for everybody is that you probably want to README to just change the README to whatever this private experiment is describing. Another thing that we recently implemented in RAT is that now RAT explicitly tracks its own versioning, because a lot of the times private experiments, the version of the private experiment you have is heavily coupled to the version of ratpac-2 that you have. So you can configure this in CMake to have it such that it compiles only with an explicit version of ratpac-2. You choose to do so. You can do pretty good version control using this command that I didn't know about 6 months ago, called git describe, which allows you to sort of track the version of your code automatically using git tags, which is pretty useful. This is what we do in Rat. This is what we do in EOS. You can also accept a formatting configuration. We have this in ratpac-2. You might notice, little CI is running when you submit code to ratpac-2, and it's complaining to you that your code doesn't follow the code style that we're enforcing. You could do the same thing in your private experiment. You can just copy the one in ratpac-2 if you like the ratpac-2 style, or you can change it however you want. Do that, and that could be helpful when you have a lot of people contributing to the same experiment. Some good practice. This is just generally how we do things in EOS. You don't have to follow this, but it's probably a good idea to do these things. So in C++, you should probably use a separate namespace for all the experiment-specific code, because very quickly you realize a lot of the code you write start to overlap with some of the rat methods and classes that you have. So we use a different namespace for all of our code in EOS, and it's probably bad. Yeah, do not use the rat namespace in the private experiment unless you sort of have to. It might be a good idea to set up a directory structure very similar to rat under your source code. So in rat we have source, and then under source there's code for different types of things that are working in rat. Like there's the geometry stuff, there's the fit stuff, there's calibration stuff. You might want to do the same thing in your private experiment, especially as the code base starts to grow. In a lot of the cases, a lot of private experiments might use fitters as more complex things that uses different dependencies. It is a good idea to guard those dependencies with these preprocessor controls, so that optional dependencies, if TensorFlow doesn't exist, do not build my fancy machine learning processor. Stuff like that might also be a good idea. So we also have experiments. We have examples for all of this in ratpac-2, and if you talk to anybody in this room who works on EOS, we're happy to show you how we do this in EOS as well. All right. So perhaps a more important thing in the private experiment is how to configure your own geometry. We talked pretty extensively, and I think a lot of you have tried, creating your own geometry using .geo files. So you could do the same thing in the private experiments. So basically, you should think about the ratdb directory in your private experiment as effectively the same ratdb directory in ratpac-2. So you would put the ratdb / name of your experiment, and then the experiment .geo file is sort of the convention in ratpac-2 where we do things. Go back to the talk that we did in geometry to sort of get more information on how to write a geo file. So if you're lucky and your detector geometry is made of pretty simple shapes, you don't have to write a factory, which is a good thing, which means that you can just use the geo files as is and not have to write Gen 4 C++ code. But most likely, you would need to create some sort of geometry factory to create more complex shapes like Boolean solids, or an array of things that you need to create, stuff like that. So you could you can create a new geometry factory inside your private experiment and adding it to ratpac-two. So you don't have to add a geometry factory into rat itself. There's a couple of things you need to make sure that you add that to the .cc file that creates your executable and the configure file. So this is just for documentation purposes to just show you where the geometry factories needs to be registered in a private experiment. Some advice, a lot of times you just want a very custom shape, but it's just one thing that needs to exist in your detector. It's not some multiple things that you need to create. You can probably just extend the GeoSolid factory and in rat and just do that and just override the construct solid class method. Sorry. But if you want an array of things, such as you have some custom PMTs or photosensors, if you want to, I don't know, deploy a bunch of ropes in your detector, for example, you might want an array of solids. You would look at a solid array factory. It's very similar logic to the solid factory, but it creates an array of things, which might be helpful. This is just to show the EOS geometry. So we use standard geometry objects for most things in EOS. We have a cylindrical outer water tank, and so that's just a G4 tube. We have rings everywhere, to sort of fasten things in place, and these rings are also standard Gen 4 shapes. We have a PMT array made of PMT models that actually exists in ratpac-two because we use mostly R146088, which is a commercially available PMT that Hamamatsu sells. So these things you should be familiar with from the geometry session and just playing around with geofiles in general. But we do have some custom geometry factories. So mainly in EOS there are two. The first thing is that our inner vessel is sort of this complex shape. So I'm showing the CAD drawing the engineers made during commissioning here. You can see that it has a sort of cylindrical middle section and it has spherical caps and it has these flanges on the top. And so that's a relatively complex shape. So we write custom code to create this shape for our inner acrylic vessel. To just make the cylinder, add it to the spherical caps and stuff like that. And we should remove this from ratpac-two, but actually, if you look, there is a EOS factory still living in rat that we mean to delete, but we haven't done that yet. Before we do that, feel free to take a look and just see what this geometry looks like. The other thing are these things called dichromicons, which are these spectral sorting devices. So devices that sort the photons coming in via wavelength. It's a light concentrator made of dichroic filters. These are basically filters that reflect light at certain wavelengths and transmit light at different wavelengths. So it looks pretty cool. So that's why I'm showing the picture here. Tanner, by the way, is the person who came up with this idea 10 years ago at this point, like that. So these things are also very custom shaped. So we also create custom geo factories for that. Here's some examples of the geo EOS factory. So as I've mentioned before, you just create these independent shapes for the body of the tube, the body of the tank, the head and the bottom. You weld them together using a G4 union solid, blah blah blah, and you create this G4B solid that looks like EOS. The dichromicon array factory, because we need to create more than one error detector, is a little bit more complex. I'm showing some code snippets here, not the full code, because it's quite long. Because the dichromicon shapes is relatively complex, we actually do not, manually describe what they look like. So instead, we just import these basically from a CAD file that the engineers has provided us into Gen 4 using Gen 4 this thing called Gen 4 tessellated objects, which is effectively allows you to create a solid using described by triangular meshes in like standard CAD like SDL files and stuff like that. This is a sort of involved process outside of RAP. So I'm just gonna briefly describe it, but this is sort of is out of the scope of ratpac-two itself. But you can create a STL from any CAD software. It's usually pretty straightforward. There's this thing called FreeCAD, which runs at least on Linux. I don't know if it runs on Windows or Mac, but there's a plugin in FreeCAD that allows you to convert a CAD file into a GDML file. in Gen 4, which allows you to then import that into RAP, should you choose to do so. Yeah, so that GDML file is read by your simulations, and then it's an array factory, so it's placed multiple times around different PMTs. Yeah. Yeah, so RADDB, obviously, you will want, you probably want some RADDB, private RADDB entries into your private experiment. We've talked about this quite extensively in the RADDB and photon propagation material properties session. So these fields should look familiar to you, perhaps, at least, the shape that they take. You probably want some experiment specific material that may or may not be available already in ratpac-two. You might have some custom fitters you want to configure, so that could also be useful for this. I will mention a couple of things about this. The first thing is that every single RADDB object can be run specific. So you can define a run number where these entries are valid. So I'm showing on the right an example of how this is part of a calibration for EOS, where we have tubes that are on or off depending on whether people have went in to fix electronics or a tube has just randomly died at some point. And so you can see that we have an array of what to describe what channels are online, what channels are offline, and these every single one of these entries have a run range key, which describes at which runs these are valid. And so when you run RAD or EOS or any experiment, you can use the -R flag to describe what run condition you would like to simulate in RAD. That's very, very useful. Another thing I would like to remind people is that even though it's in a private experiment, the RADDB folder inside your private experiment effectively is considered the same folder as ratpac-two's RADDB directory itself. So that means that if you have two overlapping table names and indices, those two things, it's indeterministic which one will be actually loaded and actually be considered true in RAD. So it's effectively undefined behavior if you have overlapping table entries between ratpac-two and your private experiment. The only exception to that are files in the RADDB / your experiment name again, RADDB/EOS, RADDB/validation in ratpac-two, for example. Those files were guaranteed to always be loaded last. So if you want to overwrite an entry in ratpac-two, make sure you put those entries into that directory rather than the main RADDB directory. And so but some things could probably just go into the RADDB directory general. Stuff like materials probably you don't need to override the material, hopefully, in ratpac-two. But some of the things you definitely want to override, stuff like calibration data, things like that. Does that make sense to people? This might be a little bit confusing. Okay.
What's an example of something you would override?
With an example,
Suggesting materials, maybe, yeah.
Materials, yeah, you could, if you did some measurements of the specific type of water, detector that could look different than regular water, for example. These channel online, these are channel step status. These are actually overrides from the default, where the default is every tube is on. So that's also an override. Yeah, I think that's all we override at the moment. I can't think of anything else. Do you have any things like?
Yeah, maybe if you want, there's a PMT that has some behavior in ratpac, but on the benchtop, you've measured it to be a little differently.
Right.
So maybe you override the PMT properties for your PMT.
Right.
But I would also recommend if you are finding yourself overriding a lot of tables, you should start thinking about maybe I should just contribute this to ratpac and maybe ratpac's problem.
Yeah.
Was the issue of priority ever fixed?
That's what I was just describing.
Okay.
Which was that if you put it in the experiment directory, that has the highest priority always. Yeah.
The one that's loaded last.
It's the one that's loaded last, so you will override everything else that has loaded before.
Yeah.
Yeah. Yes, you can also add new processors, which could be useful. It is relatively straightforward to create a new processor. It's very, very similar to creating a new processor in ratpac-two itself. You need to override the event or DS event methods, begin and end of run, like Sam described yesterday, to implement whatever logic you want the processor to actually do. Yeah, and so instead of instead of putting them in directly in the rat processor block manager, you would add a line in your main private your private experiment script that appends it to the processor via method instead. And yeah, so it's pretty straightforward to do that. So I'm showing here an example of a very simple processor that we wrote recently for EOS. You can see that it's it's a very simple thing, relatively speaking.
Why would you write a separate processor from ratpac?
Yeah, so an example of that, it could be that so in EOS, for example, where the specific fitter is trying to implement our event cleaning logic. So there are some events that our detector has triggered we don't want to actually be included in our physics analysis. That could be a very detector specific thing. For us, it could be that we have to handle crosstalk in a certain way, or we have to handle what would happen when some muon directly hits the PMT or stuff like that. And that could be very experiment specific. And you definitely you probably want something like that. That's special to your experiment to process your data. That's an example of something like that. It could also be some custom fitter that you have written that's meant you can use only for something like EOS, and perhaps it's not super generalizable to everything else. So for example, we have EOS fitters that handle that has likelihood for every single PMT in our detector, and that's okay for us because we only have less than 300 channels, 300 PMTs. But if you extrapolate that to something like Super K or Snow, that could be a likelihood that's terabytes large and probably won't run very well. So something like that, we'll probably not think about putting into ratpac if it's not, we consider it to be not very helpful to somebody else. Yeah. So this technique also works in rat, but this is a very cool thing that could be very helpful if you have a lot of people looking at data and they're trying to write similar things. So macros are the same as you would run them in rat. These are familiar lines in macro at this point, hopefully, where you describe what experiment you're running, what geo file you're using. But at the same time, you can have these things, what we call snippets, but really they're just small macros. And if you remember from Garrett's talk on the very first day, one macro can actually call another macro. And this could be very helpful if you say you have, for example, in EOS, we do this for our standard waveform analysis chain, where we always want to run these specific processors in this very specific order with these very specific configurations. And so you might want to do this so that somebody else who's just looking at data, who doesn't really care about how the waveform analysis is done, can just include that snippet in your main macro. So you don't have to worry about so not everybody has to worry about every single detail about how the macro is run. And then so on the left here is how you would include a snippet in a macro. So it's pretty straightforward. And we found it to be very helpful, especially with these standard workflow chains that we have. We have these for waveform analysis, but we also have them for fitter configurations. And that's also important because you might want to run a fitter that takes another fitter's output as the input. And so you want to make sure that the seeded, the rough reconstruction fitter runs first. Yeah. You can also extend the rat ntuple class to include detector specific fields. So we've aimed to make this relatively straightforward. We've included methods in the rat out ntuple to actually, they're meant to be extended by a private experiment to add their own fields. So we have this fields called assign additional address. These lines in these can be used to, in this method can be used to add new branches to your root trees. You can do the same thing for the meta tree. And there's fill event, fill no trigger event, and fill meta, which you can use these methods to add additional event level or meta level information to your ntuples. As an example of how we do this in EOS, you can see that we have something called the EOS ntuple that extends from the rat out ntuple. And then what specifically what we do with them is that we add information about our calibration data to the meta tree because of the way we have the calibration sources set up in our simulation. This is very helpful for us. And yeah, so that's another thing you could do. I will say that, yeah, so this is one of the primary limitations right now with extending ratpac-two as a private experiment, is that you can't easily change the rat.ds fields in the private experiment. So you know, the rat.ds files classes are explicitly defined in ratpac-two itself, and if you want to add a new field to the DS, that would be challenging. In fact, you would have to, you know, contribute that to rat and add that change to ratpac-two itself. So a couple of things you could do to circumvent this is that you could rely on existing fields, obviously, sort of keep track of processor outputs. We aim to make the DS files, the DS structure as generalized as possible, so that you know, I would say 90% or 80% of the times probably, you should be able to find a field that fits your need in the DS already. And if not, talk to us. We're probably happy to add those fields to ratpac-two already as well.
Maybe give me an example, the Liquid O example where they added the nested tubes.
Yeah, for sure. So Liquid O previously contributed to ratpac-two because they have these they would like to create these you know, wavelength shifting optical fibers, which are sort of a new type of photosensor that we don't really have support. We didn't really have support for in ratpac-two. So what they had to do was they contributed this this logic to ratpac-two itself, and at the same time we now have specific classes in the DS structure to capture information about these fibers and how they're constructed, what light they're seeing, stuff like that in ratpac-two.
So yeah, while that would naturally be a place where you might want to use private code to, since that's not necessarily something a lot of experiments are going to use, you can't do that right now. Anything that needs to manipulate the data structure has to go into ratpac-two.
Yeah, that's right. You could, but it's another thing you could do. So this is kind of a hack, in my opinion. But you could do, what you could do is just leave your processor output as global variables in C++. This is very bad practice, right? But this is something you could do, and then downstream another processor could just grab those global fields. Obviously, you know, this is a hack, and it could lead to very dangerous memory problems down the line. We're looking into fixing this. We're not sure if there is a solution because of how the rat.ds structure interacts with root itself. But it could be tricky. If you're interested in looking into this, contributions in this is definitely welcome.
Yeah, I mean, I think for the most part, we're happy to extend the data structure for even experiment specific things, particularly if we extend the prune processor that allows other experiments to prune out things from the data structure. So you can prune out, for example, all of the nested tubes, as they're called, all of the Liquid O specific tubes.
Right.
And then you don't actually get it in your output file.
Right. Yeah, and that's pretty much it for setting up a private experiment. Are there any questions about everything I talked about?
You stop the recording, stop the recording.
Emma still giving a talk?
I'll give it for.
Oh, okay, right.